Hi everyone. So in this video, we're going to be seeing how linear functions can be used to represent real-world situations, and we'll be focusing on what the slope and the y-intercept tell us about real-world situations. So before we get into that, I'm going to have you do kind of a warm-up problem. And at first, this might seem a little bit unrelated, but we'll see that it does actually tie into what we'll be talking about today. So what I want you to do, and I encourage you to pause the video to do this, is to find the average rate of change. And we're going to actually find the average rate of change for two different functions, and for each of those two different functions between two different points, or like between two sets of two different points. So I'll write that down. So the first function we're going to do is f of x is equal to x squared. And first, we're going to do it from x is equal to 1 to x is equal to 2. And then we're going to do it from x is equal to 2 to x is equal to 3. And then the second function we're going to focus on is the function g of x is equal to 3x minus 2. And so then we're going to do the same to sets of x values. So basically finding the average rate of change in the same parts of the graph, but with two different graphs. So I'd encourage you to pause the video, try this yourself, and then we'll go over it together. Okay, so let's go in and do these. Let me switch colors here. So let's start with the first one. So if we wanted to find the average rate of change of f of x is equal to x squared from x is equal to 1 to x is equal to 2, that means that we're evaluating f of 2 minus f of 1 over 2 minus 1. So f of 2 is, our function was just x squared, so 2 squared is 4. F of 1 is 1 squared, which is 1. And then over 2 minus 1, that's going to give us 3 over 1, or 3. And then if we do the same thing now with the other 2 points, so that's f of 3 minus f of 2 over 3 minus 2. So again, plugging into our function, f of x is equal to x squared. F of 3 is going to be 3 squared, which is 9. F of 2 is going to be 2 squared, which is 4. And then we're dividing by 3 minus 2, which is going to equal 1. So we're going to have 5 over 1, and so we get an average rate of change of 5. So we'll, in a moment, kind of talk about why was it that I had you do this function and what kind of the significance is of those answers. But let's do the other one first. So the other function was g of x is equal to 3x minus 2. So we're going to start with, again, from x is equal to 2 to x is equal to 1. So that's g of 2 minus g of 1 over 2 minus 1. So what do we get when we plug 2 into this function? Well, g of 2 is going to be 3 times 2, which is 6, minus 2, which is 4. And then what happens when we plug in 1? Well, we get 3 times 2, or 3 times 1 is 3, minus 2 is 1. So actually, kind of coincidentally, we actually get the same outputs as we did with the other function, but that's not really the important part here. So we get 3 over 1, which is 3. Okay, so last one is we're going to do now same linear function, but now from 3 to 2, or from 2 to 3. So g of 3 minus g of 2 over 3 minus 2. Okay, so what do we get when we plug 3 into this function? Well, we would get 3 times 3 is 9, minus 2 is 7. So 7 is our value for g of 3. And then g of 2, we already did that above, right? We got 4. So 7 minus 4 divided by 3 minus 2. So that's going to be 3 over 1, which is 3. Okay, so the reason I had you do this is I wanted to really point out that, notice that for the first function, depending on where we choose to find the average rate of change, we get different results, right? So we got 3 for the first part and we got 5 for the second part. But then when we did the linear function, we got the same result for both of them. So I want to look at the graphs of these functions and try to understand what that is. What is it about a linear function that causes this to happen? So let's start by looking at the parabola. This is f of x is equal to x squared. So the first 2 points we were looking at was between 1 and 2. And so we saw that between 1 and 2, we had an average rate of change of 3, which means basically if you were to connect those 2 points with a straight line, you would get a slope of 3. And I know it kind of looks almost like the graph itself is a line. It's not. It's a very steep curve, but if you look carefully, it is curved. So, when I go and I draw this line, it almost looks like it's just perfectly overlapping with the parabola, but it's not really. If you were to really look closely, you would see that the parabola is curved. And then the second part we were looking at was from 2 to 3. And so from 2 to 3, we have our point here, and then we have our point here. And this time, the slope came out to be 5, right? The average rate of change was 5. And so what's going on here is that the graph is getting steeper as it goes, right? Like, remember that average rate of change kind of tells you the general trend of how steep the graph is, where it's heading. And so if the first part has an average rate of change of 3 and the second part has an average rate of change of 5, that means the graph is getting steeper. It's going up more quickly. Now, on the other hand, if we look at our linear function, so for this one, our first 2 points were actually the same. It was 1, 1, and then the point 2, 4. And the average rate of change was 3. Now notice that here, if I try to draw like the secant line between those 2 points, it actually is just the same as the line, right? Like a secant line is drawing a line between 2 points that lie in a graph. Typically, if your function is curved, that line is not going to be the same as your function, right? It's going to be kind of this approximation of your function. But in this case, because our function is a line itself, the secant line is just the same as the function. And so when we go and do the slope on the next part, we get the same slope again, right? We get 3. So let me kind of summarize what happened here, which is that for the first function, which is a non-linear function, basically the average rate of change is going to vary. It depends on which 2 points you're picking. Whereas for a linear function, no matter what points you pick, the average rate of change is always the same. And so that's actually that's how I kind of want you to think of linear functions. That's what I think is actually a really good definition for a linear function. A linear function is a function where no matter what points you pick on the graph, the average rate of change between those points is always going to be the same. So I want to kind of write that down below here. So basically what we just said is that for a linear function, they have the same average rate of change between any 2 x values. It doesn't matter which x values you pick. And so because the average rate of change is always the same, we don't really need to call it the average rate of change. So the reason we called it the average rate of change for nonlinear functions was because, remember, for a nonlinear function, it's kind of an approximation. So we saw some examples of this in our average rate of change video. Depending on what your function is, the average rate of change might actually not really approximate the graph that well. So it's just an average. It's just kind of telling you the general trend. But for a linear function, the average rate of change is exactly measuring perfectly what's going on with the function. And so we don't need to use the word average. We can just call it the average, or we can just call it the rate of change. So we can just call it the rate of change. And then this is kind of what I think is maybe the most important part. So what is the rate of change equal to? If we look back at our linear function, it's the same as the slope, right? The rate of change of your function is the same thing as the slope. So we can just call it the rate of change, and it is, or I'll say it is equal to the slope of that line. So that's really what makes linear functions special, is that they are good for representing situations where the rate of change is always the same. Now, we'll see this a little bit when we get into some examples, but not every situation in the world is like that. So for example, in our average rate of change video, I showed you a graph that represented someone driving, right? And or maybe think of the temperature graph, right? Where it goes up and it goes down. And sometimes it's increasing, sometimes it's decreasing, sometimes it's steeper, sometimes it's less steep, sometimes you're driving faster, sometimes you're driving slower. Those are situations that would not be good to model with a linear function. Linear functions are good for representing situations where the rate of change is always the same. So I'm going to write that down, and then we'll jump into some examples and get into seeing how the slope and the y-intercept kind of show up in those situations. So linear functions can be used to model. And so when I say model basically just means to kind of represent, but it's just sort of acknowledging the fact that typically when you write a function to represent a situation, it's generally not going to be absolutely perfect, right? The real world is messy. Numbers aren't going to be exactly what you expect them to be. And so the word model just kind of means that we're approximating. We're going to do our best to use these functions to represent these situations, but they might be a little off. So linear functions can be used to model situations in which the rate of change is always the same. So we'll see in a moment, some examples, but just to remind you, what do I mean when I say rate of change? So we did some examples like this in the average rate of change video at the very beginning. So we saw that the rate of change is basically a description of how much a quantity is changing as time goes on. So examples of rates of change could be miles per hour, degrees per hour. On the worksheet, I gave you something about typing, and it was like words per minute. And it's not always going to be time. Often it is, but we'll see some examples in this video. Actually, will we? I think actually all of our videos or examples in this video, I think will actually be about time. So it's just how much a quantity is changing as time goes on. Okay, so let's jump into an example. And what we're going to do in this example is I'm going to give you a function that represents a situation. And I want to kind of, from that equation, from that function, figure out what's actually going on in that real world situation. So suppose that the volume of water, so volume is like a three-dimensional measurement. And so we're measuring that water in gallons in a pool after T hours is given by the following function. So let's say V of t is equal to 5t plus 200. And so what I want to answer here is I want to kind of try to figure out what is the significance of the slope and the y-intercept. I want to explain what do those two numbers tell us in terms of this situation. Okay, so there's a few ways to think about this. I think that actually making a table can be a good way just to get a better handle on what's actually going on here. I think sketching the graph could really accomplish the same thing, and I will show you the graph in a moment, but I want to actually just start by making a table because I think that might help us sort of see what's going on. So we'll plug in 0, 1, 2, 3, just a few numbers just to kind of get a handle on what's going on. Okay, so if we plug in 0, we would get 5 times 0 plus 200, and so that is going to equal 200. And then if we plug in 1, we would get 5 times 1 plus 200, which is 205. If we plug in 2, we get 5 times 2 plus 200, which is 210. And if we plug in 3, we get 5 times 3, plus 200, which is 215. So what are these numbers telling us? Well, remember again that T represents the number of hours that have passed. And then what does the output represent? The output represents the amount of water in the pool, the number of gallons of water in the pool. So what does this 5 mean, right? We have the slope being 5. So the slope is equal to 5. And so what is that telling us about this situation? Well, if we look at these numbers, what's happening is that every time an hour passes, the amount of water increases by 5 gallons, right? And so what is the slope telling us? It's telling us the rate at which the pool is being filled. It's telling us how many gallons per hour of water are going into the pool. And so I'm going to add those units here, and I'll in a moment tell you how you could know for sure what these units were. But what I really want to get at here is, what does this tell us? This tells us really it tells us the rate of change of the volume of water in the pool. And I'll kind of rephrase that in a second. But I just want to write it in terms of rate of change because that's what we were kind of initially talking about in this video. And another way of thinking about that is the rate at which the pool is being filled, right? Because the amount of water in the pool is increasing, so the pool is being filled. So by the way, how would you know that the units for the slope would be 5 gallon or would be gallons per hour? Well, remember that slope is supposed to be a change in your output over a change in your input. And so what are the units of the output? Well, the output represents the number of gallons in the pool, right? So if you're literally calculating slope, the units of the vertical change would be gallons, and so that's why gallons ends up in the numerator. And then the units of the change in time, that would be hours. So we end up with gallons per hour. So the slope basically just tells us, the rate of change, how much is this quantity changing? Okay, so what does the y-intercept tell us? So the y-intercept in this case is equal to 200. And what does that represent, that number 200? What would be the units on that 200? Well, 200 is a output value, right? And it's the amount of gallons in the pool. So it's 200 gallons. So what does that represent in terms of this word problem? Well, it tells us the initial amount of water in the pool. So where am I getting that idea from? Well, if we look at our table, 200 is what we get when we plug in t is equal to 0, right? And so t is equal to 0 represents your starting point. And so this kind of idea is going to play out in all of the examples we'll look at in this video, which is that the slope, as we said, represents some kind of a rate of change, whereas the y-intercept represents some kind of like a starting point. And we'll see that the meaning of that will vary depending on the context, but it will always represent basically whatever the situation is when t is equal to 0. So you can kind of think of that as an initial amount or a starting amount. And again, we'll see that vary as we go on. But let me just kind of summarize that. So in general, if a situation can be modeled by a linear function, the slope represents the rate of change. And I know, again, that's kind of a vague word because it really depends on the situation, what that means. But hopefully in this video, we'll see enough different examples that you can get an idea of what those might look like. And then the y-intercept that's going to represent the initial amount. Again, that will very much vary depending on our situation. Oh, and actually, I didn't pull up the graph, so let me just real quick show you the graph of this function. So the pool filling function that we just had here. So this is what that graph looks like. F of x is equal to 200 plus 5x. So what you can see is that 200, right, is our y-intercept. That's the starting point of the amount of water. And what we can see is that as you go up, increase the number of hours, the amount of water in the pool is increasing. And that's why that's the reason the slope is positive, right? And so specifically, if we look after 1 hour, it's a little hard to see here, but after 1 hour, we can see that we're at 205, 2 hours, we're at 210, etc. So it keeps going up by that rate of 5. Okay, so we're going to do just a few more examples along the same lines. But we're going to kind of, in some of them, so the next two we're going to do, I'm actually going to kind of describe the situation and we're going to come up with the function. So we're kind of reversing the process of the last one. Okay, so suppose you are, I'll not write the word suppose, let's just say you are. So you are driving home from work, or driving home, sorry, not from work. So let's say you're driving home from some kind of vacation. And let's say that you start off 300 miles from home. And then you drive at a constant rate of 60 miles per hour. And so what we want to do is we want to write a function that gives your distance from home after t hours. So before we get started, I should acknowledge that this is kind of an unrealistic situation. It's pretty rare that you would be able to drive at a completely constant rate for an entire drive, right? Maybe if you're just on a stretch of highway and you put on whatever it's called, like cruise control. But you're probably not gonna be able to drive from somewhere else to your house at 60 miles per hour the whole time. So this is what I'm getting at with this modeling idea. This isn't a very realistic situation, but it could at least give us some idea of what your trip might look like. Okay, so let's think about, kind of working backwards from what we did last time. So we know that the rate is supposed to be our slope. So we see that we have a constant rate. So constant is what tells us that a linear function is a good choice, right? Because linear functions represent situations where the rate of change is always the same. So this tells us that our slope should be something related to 60. And we'll see that there's a little bit of kind of figuring out that we need to do with that number, but we'll get there in a moment. And then we see that we start off 300 miles from home. And so that kind of sounds like it's your initial amount, right? Because what is this function measuring? It's measuring the distance from home. And so since the amount that we're measuring is the distance from home, the initial amount should be your initial distance from home. So that tells us that the y-intercept should be equal to 300, right? Because we want to make sure that when t is equal to 0, the distance from home is 300. Now, what is the slope going to be? So this I think is a little tricky, and I'm actually going to do this incorrectly first and then show you why it's incorrect. So you might guess that the slope is 60, right? That seems reasonable, right? We said that the rate is supposed to tell us the slope, so the slope seems like it should be 60. And so that would give us a function of, we can just call it f of t, or maybe let's call it d of t because we're talking about distances. D of t is equal to 60t plus 300. Okay, so let's see why that is actually wrong. So, oops, and I actually typed this wrong. Give me 1 second. I think I might have in my notes said 50 instead of 60. Okay, so this is the graph of 60x plus 300, which is what we just said, might be our correct function. So does anything stand out that might be wrong just by looking at the graph? And remember that the story is supposed to be that we start off 300 miles from home and we're driving home, and we're supposed to be measuring how far we are from home. So to me, what stands out is that if you're driving home, you should be getting closer to home, right? As time goes on, your distance should be getting smaller and smaller because you're getting closer and closer to home. And so what's going on here is that we start at 300 and we're driving 60 miles away from home per hour, right? So this would be the graph if you start 300 miles from home and you keep driving away from home. And so this is actually not the correct function. So let me kind of make a note of that, and then we'll write the correct one. So this is wrong. So this would be, this would represent driving away from home. So really, what should the slope be? Well, it should be negative 60, right? Because, one way of just thinking about it is that if you think about what the picture, what the graph should look like, it should have a negative slope, right? Because we should be getting closer and closer to home. And so that will give us a function of d of t is equal to negative 60t plus 300. And I'll pull up the graph of that in a second. I just want to mention, how else might you know that the slope is going to be negative? Well, if you just kind of think about, what is this function representing? It's representing the distance from home after t hours. And so your distance from home is actually decreasing. And so that's another way of thinking about why the rate should be negative, because you're not talking about a distance that's increasing. If your distance was getting further and further, then the slope should be positive. But when you're representing a real world situation that involves something decreasing, the slope should be negative. And so, you don't see the word decreasing written in this story, but because your distance from home is getting smaller as you drive closer, that tells us our slope should be negative. So this is actually the correct graph. We can see that this one starts at a distance of 300, so that's your starting point. And then as time goes on, your distance towards home or from home gets less and less, and after 5 hours, you actually arrive at home. Now, as I said, and I'll actually put a question kind of like this on the worksheet, this is not really realistic for what your travel would look like. Most likely you would go faster and slower at different parts. So again, I just want to really emphasize that linear functions are best representing situations where the rate of change is always the same. And that's not necessarily really going to be true for a typical car ride. Okay, so we're going to do another problem kind of along the same lines. So let's say that you have a lawn mowing business. So the way that you charge is that you charge an initial fee. So it means that no matter how many hours of mowing lawns you do, everyone is going to have to pay this initial fee of $8. And then on top of that, you charge an additional $6 per hour of mowing lawns, which I don't know, maybe you live in a neighborhood where people have really big lawns, because I can't imagine that you'd have to spend that many hours, but I guess, I don't know, I don't even have a yard. Okay, so let's try to figure out from this, what is going to be our slope and what is going to be our y-intercept. So we see this, this word initial. So initial should make you think of, starting amount, the initial amount. So it kind of seems like the y-intercept should be 8. And another way of thinking about that is the y-intercept is basically the thing that isn't changing in a sense. It's so, the everyone gets charged $8, right? That part doesn't depend on how many hours of lawn mowing you've done. Whereas the next part, the $6 per hour, well, that's the part that is going to vary, right? That's what tells you the rate of change, essentially, the rate of money that you'll be making per hour of lawn mowing. And so this $6 per hour is going to be our slope. And another good hint, and let me even write this out in words, I mentioned this in an earlier video, this word per kind of corresponds to division, right? Miles per hour. You all can also write as miles divided by hours. That word per should always make you think of a rate of change. And so when you see $6 per hour, it's like, okay, that is my rate. Okay, so that tells us that our y-intercept is going to be 8, and our slope is going to be 6. And we'll see that the slope should be positive in this case, because the more lawns you mow, or the more hours you spend mowing, the more money you should be making, right? And so it makes sense that this is going to be an increasing function, so the slope should be positive. And so maybe we can call our function C for like cost. So the amount you'll be paid is going to be 6t plus 8. Okay, so let's look at the graph and just kind of make sure it aligns with what we expect. So here's what this function would look like. So we can see that if you just go to someone's house and just look at their yard, you still get $8 with no mowing. But the more hours of mowing you do, the more you get paid. And we can see that by mowing for an additional 1 hour, you get an additional $6, which corresponds to our slope of 6. Okay, we're going to look at one last example. So this example is going to be kind of like the first one in that we're given the function. This time we're given it as a graph instead of as an actual formula, but we're going to need to kind of make sense of this situation. So suppose that this is a function, let's call it h of t. So the function, I'll start by saying this, that you are on a hike. So the function h of t gives your elevation. So elevation basically means your height, how many feet off the ground you are. After t hours. And so basically what I want to do on this one is make sense of this story. What is happening? How would we describe this hike? What is the y-intercept telling us? What is the slope telling us? And how can we kind of put those together to tell us what's going on in this situation? So first of all, let's actually find the y-intercept. So the y-intercept for this function is 2,000, right? And so the y-intercept is equal to 2,000. So what would the units of that be? Well, the function tells you your elevation in feet, right? And so the y values on this graph are representing a number of feet. And so our elevation, or our 2,000, our y-intercept is measured in feet. So what does this tell us about our situation? Well, remember that we're supposed to have the elevation after t hours. And so the elevation after 0 hours is 2,000. And so that actually tells us our initial elevation, right? That tells you where you're starting. Okay, so what is the slope of this graph? Well, we can figure it out by looking at it and maybe taking a couple points. So we can see that we have this 1 point already, right? We have the point 0, 2000. We also have the point 1, 1000. That's probably like the easiest other point to look at. So what is our slope going to be? Well, if we look at the vertical change between those two, it's 1000, right? From 2000 to 1000 is 1000. So the vertical change is 1000. And then the horizontal change is 1, right? We're going from 0 hours to 1 hour. Now I want to put units on this, and then there's something else that we're missing. So what is wrong with what I have right now? Well, the slope should be negative, right? It's going down. And so that's what I was saying earlier with, or in the last video, with when you're finding the slope from a graph, it's very easy to make mistakes with the sign. So just look at your graph and make sure that you have the right sign. So this should be negative. So we're going down as time goes on. And then what are our units? Well, remember the outputs of this function represent the elevation in feet, and the time represents the number of hours. And so this tells us that our slope is negative 1000 feet per hour. Sorry, my screen is a little stuck. I'm trying to scooch over because I think I'm probably going off the screen a little bit. There we go. Okay, so what does that tell us about our situation? Well, that's supposed to tell us the rate of change. So I'll first write it like that, and then we can kind of turn it into something that is a little more meaningful. So the rate of change of the elevation. So what does that really mean? What does it mean to have a rate of change of negative 1000 feet per hour? Well, that means that we are descending. So we're descending. And why do I say the word descending? Because the rate is negative, right? We're going down. So I'm going to actually say at a rate of 1000, I'm not going to put the negative sign, because when I say descending, that already kind of suggests that it's negative. If you really wanted to, you could put a negative sign there, but I think basically just by saying the word descending, that kind of includes the negative in it, if that makes sense. Okay, so what does this tell us? This tells us that we're hiking downward, right? And so what would be going on in this situation? Maybe this is the way back on a hike. Maybe you've already reached the summit and you're now on your way back. And so as time goes on, after each hour, you've gone down by 1000 feet. All right, so that is it for this video. And like I said, in the next video, we're going to be talking about one other way of writing the equation of a line, which we'll see is just kind of a useful additional method to have in your toolbox of linear function skills.